let's talk about the law of sines and the law of cosines. Now, before we understand the formula, we need to first draw a triangle and learn the convention for labeling the sides and the angles, because those labels are what are used in these formulas. If you change the way you label your triangle, your formula will no longer be true. So we're going to draw an oblique triangle. That means it has no right angles, okay? On the vertices, that is. Every vertice will be labeled with a capital letter. That is arbitrary. I can put them anywhere I want. So now across from every vertice, every angle is going to be the corresponding side. And now this is not arbitrary. It has to be the lowercase version of the angles letter. So think of this as mama and child, okay, or papa and child. So capital A is always looking out to supervise its child, little a. Angle C is always looking out to supervise little c, and angle B is always looking out across to supervise little b. All right, now having done this, we can write the law of sines. It simply says that the ratio of the sine of angle A to little a equals the ratio of sine of angle B to little b, and that equals the sine of C, capital C, to little c. This law is so simple to prove that I'm going to do it for you. And let's see if I can get it done in less than a minute. Let's think about the perpendicular that we would draw in this triangle if we were going to find its area. Okay? We don't really need to calculate its area, but if you were, you would draw a height from one of the vertices down to the opposite side. That is a perpendicular, so it creates two right triangles. So now I can write that height that I just drew in terms of angle C and the hypotenuse of the right triangle. Let's do it. The sine of C, first let's just write it in terms of SOHCAHTOA. It's going to be the opposite, which is H, over the hypotenuse, which is B. So I can solve for H and get B times the sine of capital C is equal to H. But we have another right triangle right here. And let's do this one now. The sine of B, capital B, is equal to, again, H, but this time the hypotenuse is little c. Remember, the hypotenuse is always the side that is opposite the right angle. So that would be H over little c. Again, we can solve for H and write C times sine of capital B equals H. Now look at this. Both of these expressions equal H. So I can set them equal to one another. We'll do that. We will just do that. We will do that. There we go. Now, if we divide both sides by C, we will get sine of capital C over little c, and this will just be sine of capital B. Then we can divide both sides by little b. When you do that, this cancels out, and you're left with the first and last part of this equation. That's very good. Now, what about sine of B over B? Okay, well, I think I can figure this out. I know that if I draw another perpendicular, let's do it. Let's draw another perpendicular. I can create another set of relationships. There, this should be a perpendicular. So I am going to draw those right angles, and there's my second H. This is not the same H as I had before. Please be careful. I've just drawn it from a different vertex. It's probably longer. I feel like it's longer. But we can still use this to see how this comes into play. We're going to use the angle A now and write more equations. The sine of angle A times the hypotenuse of B is going to equal that other H I just drew. We'll call this H2, so you recognize it's different. This is H2. And now on the other side, again, I see angle B looking at H2. I'm going to write its equation. That's going to be the hypotenuse of A times the sine of capital B. And that is also equal to H2. Now we'll do exactly what we did before. Okay, we're going to move this to this side because they're both equal to H2, which means they're equal to each other. That's the transitive property. Aha! Now we can divide both sides by A and then divide both sides by B and end up with the other piece of our puzzle. Now, look at what we have here. We see these are equal to one another. And we see that the sine of B over B shows up here also, and it's equal to sine of C. So by the transitive property, they're all equal to one another. That's pretty amazing. Now, if I have any three pieces that are showing here in the right combinations, I can solve for the fourth piece, right? If I have capital A and little a, and any of these other angles, then I can solve for the other sides, the corresponding side. It's very important to realize that you need to have at least one matching set. You have to have either capital A and little a or capital B and little b in order to form your ratio. Without the corresponding side or the corresponding angle, you won't be able to use the law of sines. But what can you do? If I don't have, let's say I have capital A and little b, and I want to find capital C or something like that, there's nothing I can write that would take advantage of these relationships here. I'll have too many unknowns. But we have another law. I'm not going to prove this one to you, but I am going to show it to you and help you remember it. And you'll see how handy it is for the cases when we cannot use the law of sines because we don't have the right pieces. The law of sines has ratios. The law of cosines is a sum with squares. What does this remind you of? Well, it reminds me of the Pythagorean theorem. A squared plus B squared plus C squared. But it seems to have the letters out of order, right? Well, guess what? There are three versions of the cosines law, and one of them has the C squared on the outside. Then it would look just like what you're used to. But really, don't be stuck on these letters and their order because these triangles are not right triangles. There is no hypotenuse. So it doesn't matter which version of this we're using. As long as inside the formula we're using, we keep all the letters straight. It hasn't changed from when we used the law of sines. The little a is still the corresponding side to capital A angle. Now, when you're looking at this formula, you see Pythagorean's theorem. You see that there's a corresponding side and an angle, an interior angle, and those are on opposite sides of the equation. So they're kind of still mirroring each other. Then you do the Pythagorean theorem with the other two sides, but then you have a corrective factor. You should expect to have something that corrects because this is not a right triangle, so you shouldn't expect to see the Pythagorean theorem. You're subtracting away the extra here. Okay, this is actually much too much to equal a squared, right? Look, this letter C here is much longer than if I had the right triangle where this was C. That's much longer. So I'm going to have a bigger square. If I were to draw a square around this, it'd be bigger than if it was this line here. So that's why we're subtracting something away here. Okay? Think of it that way. Now, the two letters that are in this part of the equation match the two letters that are in the first part of the equation. So the A's only show up in the angle and in the left side of your equation. So we see that we can easily memorize this. A squared equals the other two letters, B squared plus C squared, minus, because we're correcting, we're taking away, this is a bigger triangle than the right triangle, 2 times BC times the cosine of capital A. Don't forget this too. If you're good at foiling, you might remember that this formula here, A plus B squared, okay, or A minus B squared, would have a 2AB inside of it. All right, remember that? It's got A squared and B squared on the other side, and then in the middle had this 2AB. That could help you remember this 2BC right here, okay? So imagine that it is A minus B, and that's when it would be minus 2AB, okay? So hopefully those clues will help you memorize this formula. Now, this is super handy when we have B, C, and an angle A. Notice that I don't have the corresponding parts when I have those three things. Notice that. I don't have that. I'm missing A, little a, which would correspond to capital A. I'm missing capital B and capital C. So that's why I could not use the law of sines, right? Now, maybe you have the other pieces. You have A and B, and you have angle C. Okay, so what would that look like? Here's angle C, and you have A and B. Notice that everything is next to each other, but you don't have anything that's opposite the other as far as you don't have any of the opposite pairs, angle C and little c, or angle A and little a. So if you ever have a side, an angle in between, and then another side, you don't have any opposite pairs. You need to use the law of cosines, because that's where you can work with things like side, angle, side, the sandwich. I call it the sandwich. Let's figure out the other formulas really quickly. So here's C squared equals A squared plus B squared, then it'd be 2AB times the cosine of which angle? Capital C, because little c is out here, so that's where capital C shows up. Awesome. And now, let's do the last one. See if you can do the last one without me. That would be B squared. And the other two letters are A squared plus C squared minus 2AC again times the cosine of mama angle, capital B. She'll always show up. Little b needs to know Mama B will never be far away. Awesome. So now we have great tools to solve all of our triangles. And with these two tools, you really can solve any triangle that exists. Happy solving. See you again another time.